In light of all that we've learned, it seems exceedingly likely that the only life that will really exist on Mars would be human life, and any other life forms we brought with us if we ever decided to settle the red planet. The question of settling the red planet permanently reminds us of some of our conversations about like societies in space and things like that. But there's another possibility we haven't discussed yet, which is very much in the realm of science fiction, but nonetheless really fascinating. That is the idea of terraforming. Terraforming is a word we associate with transforming an entire planet. So are there things that we can do to actually change the climate and atmosphere and environment of an entire planet? Now it seems that we can, because the climate on Earth has changed as a result of human activity, but can we do that intentionally and to a much more dramatic extent on another planet in order to make it habitable for human beings? So let's just play out how this might work. I've got here a nice infographic from National Geographic. They call it the 10,000 or the 1,000-year project. All right. So you could imagine starting here on the left with manned missions to Mars. Okay, and those initially involve coming back and forth for humans, so an Earth return vehicle. Then what would be sent, right, these modules that we've kind of seen examples of where people could live inside these protected environments. But then you see here factories emitting super greenhouse gases, right? So greenhouse gases like carbon dioxide, but there are also these PFCs, right? Like these things that are aerosols bad for the environment that help really make the greenhouse effect kind of get out of control, which causes the Earth to get extra warm, right? Well, Mars is really cold. So if you put a lot of those into the atmosphere, in fact, if you made factories where that was the sole thing they did is produce those kind of chemicals and release them to the atmosphere of Mars, perhaps you could do it so quickly that you could actually start warming the planet through sunlight being trapped through the greenhouse effect. And if it started to get warmer, then perhaps this ice that's sort of beneath the surface could melt and we could have more liquid there. And also pushing all this gas into the atmosphere could perhaps raise the pressure of the atmosphere so that that water doesn't immediately evaporate. So now we're starting to develop an atmosphere, right? That's the next key step after 100 years only, okay? And then what? And then, so we've got communities that are living there. It starts to become more hospitable. You've got an atmosphere, so maybe vegetation can start to grow outside of these habitats. And you've got liquid water on the surface because you have a thick atmosphere. So now a water cycle can start to happen where you have a small amount of evaporation forming clouds. You get rain to start coming. So after maybe 200 years, we could get rain falling and water flowing once we have enough CO2 in the atmosphere. And then only after a mere 500 to 600 years, perhaps we could hope to have plant life, flowering plants, trees, and flowering plants being ones that produce food, growing in the native Martian soil. Just 500 years, no big deal, right? And then our habitations, of course, get bigger and bigger, with the hope that after 900 years, we can produce our own energy for cities if a purpose and desire emerges, maybe through nuclear power or wind turbines. And then after just 1,000 years, we could be the Martians, living without necessarily whole space suits, although perhaps in this infographic they suggest we would still need to wear our own oxygen tanks, since the atmosphere would be rich in carbon dioxide to support plant life and the greenhouse effect. So it said Martians would go out only with scuba gear. Oxygen would remain low for many thousands of years. Over geologic time, before Earth itself becomes uninhabitable, Mars would lose its new atmosphere and freeze again. Which is quite striking, that this would be a temporary effect that would require ongoing maintenance for humans to do. So perhaps you're already convinced this is like impossible, but just let's look at it from a scientific point of view. So we've got a few, we're leveraging our understanding of science to try to transform this planet through the greenhouse effect and other things. A lot of those things make sense, like in principle, like they're possible, feasible. One of the concerns, though, is keeping this atmosphere. Mars doesn't have much of an atmosphere for a reason, and so what could we do to create and keep an atmosphere there? I just want to illustrate why it doesn't hold on to its atmosphere. This is a gas retention simulator. I'm sure you've been hunting for one of these, so I've got it here for you, the gas retention simulator, which simulates how atmospheres really can be held on by planets. So what I can do is I could add some gas, and now the one of interest here is carbon dioxide. So I've got gas in this chamber, and this chamber represents a planet, all right? And what's holding this gas down really is gravity. Gravity pulling on every one of these molecules of carbon dioxide. What's causing this gas to want to fly away is that it's warm. Really, any temperature that something has means it's going to be moving around, right? In fact, that's really what temperature means. The hotter something is, the faster it's moving. So what you see on this graph, forgive me, but I'm going to use a graph, okay, is the number of particles. So in this box, there's a number of particles. This is the distribution of the number of particles versus their speed. So you see a couple of these particles are moving very, very slowly. I'm just going to start the simulation here. So you see them moving around. A couple of them are moving very slowly. Some of them are moving really, really fast. Like there's one going really fast. All right, and then, but on average, most of them are going at an intermediate speed. And you'll notice they're banging into each other, bouncing around, and in general, that's what's causing this distribution. So at any given moment, one might be going slow, and then it gets boom, and it starts going fast. But on average, this is what their distribution looks like. Now, so you've got competing factors. You've got gravity trying to hold it in, and then you've got it's warm, so they're flying around and they're trying to escape. And if they go fast enough, they can escape the pull of gravity. So here's what's happening on Mars. It's extra cold on Mars, right? So if I go down to like Mars temperature, that actually helps us keep the atmosphere, right? That actually slowed down all these molecules, which means they're less likely to escape, right? That's why the gas giants are gas giants, because they're so cold. So it's easy for them to hold on to all that gas that makes up a huge atmosphere. But what's working against Mars is that it's really small, like a third of the size of Earth. So the escape speed is really small too. So if I allow particles to escape, let's go back to the original temperature here I started at, 300. Now you see the escape speed by default is way up here at 1500 meters per second. If I start the simulation, even though I'm allowing something to escape, really none of these particles are getting fast enough that they would ever cross that escape speed, right? So we're not losing much atmosphere. This is like the Earth, sort of, right? But on Mars, it's colder, so it's moving further away from that escape speed, but the planet is smaller, so gravity is less, and so that escape speed is way down here. Now, the escape speed, if it just happens to touch this distribution even a tiny bit, like this, it's catching just that tail, you might think, well, it's only going to lose like a little fraction of the atmosphere, right? You're only going to lose 5% of your atmosphere. You'd keep the whole rest of it because all these other particles are going down here. But keep in mind, this is mixing all around. So while one of these guys might be moving slowly initially, it might speed up. And the thing is, once you cross that escape speed, once you cross that threshold, you're out the door and you're never coming back. And so if I start the simulation now, what you'll start to see is if you look at this distribution of all these particles, you see how the whole distribution is getting smaller and smaller. They're sneaking out. They're like bleeding out. In fact, in the chamber here, you can see some flying out. Let's see a fast one. Whoop, there it goes. Out the door. There's another one. There's another one. And you see the piles getting smaller and smaller. So I'm losing my atmosphere. It's flying off into space. Now, as there's fewer and fewer, right, I'm going to lose less and less. It's going to happen more slowly, right? But over time, this total atmosphere is going to continue to be lost to space. And that's what happens on a planet like Mars. Now, there are other factors that give more bad news for terraforming. Here's an article from space.com. Bad news for terraforming. Mars's atmosphere is lost in space. There are other factors pushing the atmosphere away besides just merely the temperature of the gas. Actually, solar winds, so this stream of energetic particles coming off of the sun, is blasting Mars. On a planet like the Earth, we have a strong magnetic field, which protects our atmosphere so that this solar wind gets it's like a shield that pushes the solar wind away and doesn't strip away our atmosphere. You never thought the magnetic field of the Earth was like protecting us, but it really is in many ways. Mars, by contrast, has a very weak magnetic field. And so that solar wind is really just blasting the atmosphere. So here's a simulation which shows that. Here, I'll turn off the audio. Hello. Maybe I'll leave the audio on. So there's the solar wind. Okay? You see it's hitting Mars. There's not much of a magnetic field, and so this is a simulation showing ions, right, like molecules of gas in the upper atmosphere of Mars, just being stripped away from the atmosphere, being pulled away. All right, so as if Mars needed a worse situation, okay, these particles are actually being ripped out of the atmosphere. So you'll notice if we look back at our terraforming project, the very first step and the critical step is enhancing the atmosphere of Mars. And so if that doesn't happen, really none of the other things can follow. So this is a bad news bears kind of situation. Fortunately, I hear there's another planet called Earth, which is really very hospitable. But you know, seriously though, this is for those who kind of think that the future of humanity involves leaving our planet to go live on another planet, I think there's a reality check here that we have to take good care of the planet we do have, right? Because this is the one that's designed for us, that we were designed for, and all the more reason for us to be taking good care of it. So that's terraforming, cool stuff, kind of out there science fiction-y kind of stuff, but nonetheless a lot of good science involved. All right, thanks a lot, and I will see you next time.